or good morning, or I hope you're awake. I try to be. And of course, I'm very pleased to start this conference, even if it's number 2. That's great. I was in number 1 as well, for those who didn't know that. Anyway, I will talk about collective noise and complexity from finite to infinite dimension. That's a little bit, the transition to the previous talk. So there will be some infinite dimensional stuff at the end. I have a long list of co-workers. Sheng, he just finished. Pei Xu goes to Waterloo. Roy is here. And that is my former group of students, which I worked with. So I will use a little bit of all of them. In fact, that is the transition I have to make. Let's see whether that works. Plan. Okay, good. So I have a plan. I try to. And so I will tell you a little bit of the noise model, okay? So let me say something before I go through this plan. You should more think of this like an impressionistic picture, right? So I will give you some kind of topics which are blended together, and it's more about the whole picture, not about all the little details. So if you see this long list here, Lindbladian decay estimates, convex complexity, Lipschitz complexity, Talagrand type inequality, Hamiltonian approximation, results from groups, and then back to the noise. So that's a long list, and so I hope we will paint a picture and enjoy it together. If one detail doesn't really, if one detail catches your attention, I'm happy. But let's try to see this as more as a big picture than the small units. And yeah, the next thing here would be these collective noise models. And yeah, you can see me here, right? So what I see there is they draw these pictures, right? And I don't know whether you ever had that experience. I'm a mathematician, and then I read a physics paper where they talk about atom arrays, and I still feel so stupid. I mean, I just don't understand anything. It sounds all fancy. Atom array, radiance, super radiance, and these words, they're fantastic. I mean, the creativity is unbelievable, and I somehow try to make sense, just a little bit sense out of them. So what I learned is, if you have these atom arrays, which actually are used in experiments, that I'm pretty sure of. Atom arrays are still used. They're not always unitary, it's more the open system thing. What matters is the distance between the atoms, because if they get too close, they start to interact. I think I can say that I safely learned that. I hope this is still true, but and so when they get closer together, they have more interaction terms, and then you have to model this. I think this is really, so far that's really okay to say. And then they model it using the Born-Markov approximation. And yeah, I would really like to understand that. It's very, it's a very old concept from the 70s or even before they do that. And then miraculously, they end up with the Lindbladian, okay? And unfortunately, I would like to understand this twiddle better, but so far I have failed. But what do? I start with the Lindbladian and hope to understand that. But this is the good news. Certain things look okay. So here's a picture, atom arrays, super radiance, photon emission. It's really about photons, right? I mean, if they get closer together, they emit photons, and that's what you measure, and you want to know how many they are and how they interact, and then I'm not saying you have to read this all. This is what I copied from a paper, right? But it is actually critical, and there are some phenomena, super radiance, which the experimenters I know actually care about. But I'm not going to talk about them. But it's going back to Dicke in the 70s. Okay, so then here is the Hamiltonian, and that is kind of the magic, right? So the Hamiltonian then has Lindbladian form. You might have heard about generators of semigroups of completely positive maps. And then you may have heard of Lindblad, who in the 70s characterized them all on type 1 for Neumann algebras. And they have the following form, written for X being an observable, not a state, for a moment, observable, okay? A commutator and the noise part. And the noise...
No?
Huh?
It's not linear in X, no? There's an extra X.
It's linear in X.
No, the second term is not linear. The two x's.
What do you mean?
You have x, a, r.
Oh, there's a bracket here, okay? It's AR, I mean, these are coefficients, and this is the, oh yeah, you're right.
Okay.
You're right, that's a typo, thank you. That X I overlooked. I have to exit out, but if I do that, but anyway. You're absolutely right, this should be linear in X, and X goes to the right, X goes to the left, X goes in the middle. That's how I remember it. And then you have these ARSs. And these ARSs, they sound like, very abstract. I'm taking one atom. So I'm doing a very simple atom where you have only a state 0 and a state 1. And then you can go from this level to that level, right? In principle, you should also allow for some probability go back from an excited states back down. And in principle, you should allow more than one states. If you look at the interesting pictures, they have 2 or 3, and the memory is interchanging the 2 other ones. For certain rare earth metals, you can see that. For mathematical reasons, I'm doing 2. If not, I would have to work with a larger group, and that makes my talk harder, so I will not do it, but it's not impossible. So let me go through the notation slowly. There's no X. So if I write AR, I just put the A in the R's position. Very standard notation, but I will use it a lot. My easiest A is this one, like a creation operator. Whether it's creation or annihilation depends on where you put the 0 or 1, so I leave that to you. And then these matrices, they are not arbitrary. We think they're arbitrary. They really come from quantizing a Maxwell equation and the Green's operator for that. So they steal them from this Green's operator. That's really fair to say. As far as I understand these texts, that is true. The Hamiltonian is also created from the Green's operator. One is the real, one is the imaginary part. And they are also relatively harmless in the sense that they are linear combinations of these first order ARs. And that makes it good for our models. So these are physically sort of relevant, but mathematically, come on, that's not so hard, right? I mean, that is something we can actually work with, right? But it's a good noise model because, the jump operators, the ARs are local. So these ARs are called jump operator. Let me continue. Yeah, I think that I already said that. Yes, here, what's the most important trick I learned from these papers? And I don't want to degrade them, not at all. I mean, I think they're great papers. What do they do in order to make their life simpler? If you have a matrix which happens to be positive definite, what to do with a positive definite matrix? What do you do with a positive definite matrix? What do you tell your students? What do you do with a positive definite matrix? You diagonalize, right? Yeah, eigenvalues, right? There seems to be, that's exactly what they're doing, right? And then you get this simpler models, which are given by linear combinations, this diagonalization, and I want to focus on one particular thing here. My Pn of A is the sum of the AR. So in every position, I use one of the ARs. So these are my simple building blocks for the Lindbladian. Okay. So then I have to tell you a little bit. So this is a building block for the Lindbladian. Here I did it right. 1x here, 1x there, and the middle is missing. So the number. But
you were paying attention.
Yeah. Here it belongs, right? So this is always the Lindbladian form of a building block, but there is a mystery, which I also took a great time to understand, but it's very simple. It's really nice linear algebra. I stole this from Carlin and Maas. They were looking for Lindbladians whose dual operator, right, on states preserves the state. So you want to have that property L beta star of row 0, or the semigroup leaves it invariant. That goes to state preparation, right? I mean, if you have a semigroup, which after a long time gets to this fixed state, that's what you want. That's how you could do continuous approximation of a state. So you have to find a good combination of these betas to achieve that property. That's, if you need an exercise, it's linear algebra, right? And their solution to that is you have to take eigenvalues of the so-called modular operator. So if you conjugate with the complex powers to the left and right, you have an eigenvalue. It's modular operator. If you like type 3 objects in von Neumann algebras, you have seen that thing before. If you have not seen that before, you don't like type 3 von Neumann algebras. So it's a very nice mathematical structure. The eigenvalue, you have to use A's, which are eigenvalues of the ground state or basic state or state you want to refer to. And then you can create Lindbladians which at least leave that state invariant for all time. You know? So this is the noise model I want to consider, where A is this guy. And then it depends on n. If n gets larger, so we are looking at linear arrays which are getting larger and larger. We have just, we jump up and down. Now, the fact that I'm using A and A star in certain powers means that with certain probability I jump from 0 to 1, and with some probability I jump from 1 to 0. I have to do that in order to preserve a good state. So what is the state I want to preserve? I will talk about this later. Sorry for that. So I will take you later which state I want to preserve for this concrete model. But in order to understand this decay to equilibrium, I have to have some quantities to measure it. And the one quantity I use is the spectral gap. So L is here my Lindbladian, and spectral gap means that some fuzzy L2 norm can be estimated by some funny energy form. Yeah? This rho is a state which is left invariant by the dual object. Yeah, we always have some reference state. We are assuming that this has full rank, because if not, that's not very reasonable. And yeah, there's this E fix here. And that is the weakest point of my argument, actually, because I have to assume that the set of fixed points of my operator is a star algebra, which is a sigma details balance condition, but it's a serious condition, right? I mean, if you write down arbitrary Lindbladians, might not happen. I have to assume that if you are in this Carlin-Mass eigenvalue situation, it will happen, but in general it might not. So this is where I don't know. That's my wide territory where I'm completely clueless, right? I think there are some tendencies to learn that better, but at the moment I'm assuming that there is a fixed point, and then I'm assuming that there's a conditional expectation, a projection onto the fixed points. I'm just assuming that always exists in finite dimension, but it can depend on the state, and that's okay. I can, because if not, it would be physically unimportant, right? Uninteresting. Okay, so these are the stuff. Spectral gap is something, super classical, right? But, if that doesn't help, then you're lost. There's something stronger, entropy decay. So we call that if the relative entropy compared to the fixed point decays exponentially, we call this entropy NK. The definition is MLSI, modified log Sobolev inequality. If we do that by tensoring with an arbitrary extra system, we call it complete logarithmic. It should be complete logarithmic modified Sobolev inequality. So you see here there's an M missing. That's my fault. I decided from the beginning there is no complete log Sobolev inequality. I just decided that, and later it was proved I was right. So there is no complete version for the original Sobolev inequality. It says false for any small system. So this is why there's no M, because this is the right Sobolev inequality over logarithmic side. Yeah. So we are looking at this decay. Of course, why do we decouple? Why do we couple with an arbitrary system? Because then this log Sobolev inequality becomes stable under tensors. You want that, right? You want Taylor tensibility if you couple with another system. Very natural. That's the notion we're going to use. So we can ask for decay property in terms of entropy or in terms of spectral gap, right? Because then the semi-group on the L2 space will decay exponentially. So these are the two kind of decay properties. And now I will tell you about the results for the state I have in mind. So let's slow down a little bit. This way to write rho lambda as a tensor product, and I don't care about how many copies, right? N copies in our place, but I mean, infinite dimension will just say, I'll take infinitely many copies, and then you're in the type lambda factor. We'll talk about that again, but if you want to understand type lambda factor, you take that state, infinite tensor product on a tensor product of 2 by 2 matrices. That's not so dramatic when you do GNS completion, right? So that's not that scary, right? I mean, it's really just an infinite Turing band with this funny state. Now, this choice, lambda over 1 plus lambda and 1 over 1 plus lambda, is to make that the modular group goes out with lambda, because, you know, the ratio between is lambda. Yeah, that's the reason for lambda. And yeah, so this is our state, which is preserved by this version of our Lindbladian. I told you have to do this modular group shenanigans so that this all fits together. Here it works if I choose lambda e to the beta, okay? So this is just numerics to make things work. I'm just trying to match up, but then I don't really have a choice. And what can we say? Well, we can say that for beta equals 0, things are super nice, because all of these have a uniform spectral gap bounded below by some kind of differential operator, which I will talk about later, right? So there's some group differential operator, which has CLSI, which we can prove. And then we have a uniform bound for the CLSI constant and the spectral gap in all dimensions. Wonderful, yeah? And I mean, the work with Yidong, we started, and I always wanted to prove that's also true for beta just close to 0. And we tried forever. And we tried. And we tried. And if you try so long, what happens? You fail. It's wrong. The spectral gap is not bounded below uniformly. It simply isn't. We don't know exactly whether it's between 1 or 1 squared. I don't know. We have some example. We make some calculations. What we do is representation theory of groups, and then we go between 2 irreps and find some intermediate vectors. So if you do representation theory, the representation here is SL2, right? And you're taking tensor products of SL2 representations, and they play a big role, and then you can actually do it. So we found these examples after trying forever. I tried forever to prove that this is uniformly bounded, but then together we realized, no, it's not true. There's nothing you can do. So what this means, if you want to do physics interpretation for beta equilibrium, some kind of uniform decay to equilibrium, right? But for beta bigger than 0, you have some memory effects. You can have some non-invariant states, which up to time t properly of the order n are stable under the evolution. Right? So in principle, that's a good thing, I think, because you have more room to create interesting states. Well, that's what it means if I do this interpretation correctly, but I think I'm getting, that's not too far away from what even experiments would accept, if they accept my interpretation. Good, so now I have a problem. What do I do? I mean, I promised from finite to infinite. What do I do? Well, there is no infinite limit. I mean, the infinite is just nonsense. There is nothing to say. So I have several ways out. If you don't know what to do, you change your parameter. As a mathematician, you can do that. As a physicist, not so much sometimes, right? I mean, if you're given the system. But as a mathematician, we can. We just define new operators like that one. We multiply with the square of that operator. The jump operators are 3 local in every term. So that doesn't mean that the semigroup is, just the jump operators are still 3 local, because only three parties are involved in every term. It's not a Davis generator, though, right? These things are very far away. For those who actually know that, they are not Davis generators at all. So the whole theory of Davis generators doesn't apply, and it doesn't tell you anything. But still, now we have a uniform bound on decay. That we can prove by just reanalyzing the system and using some, actually, if some want to talk about analytical methods, one of the things mathematicians bring to the table are Schur multipliers. They actually thought about Schur multipliers for a long time, as have physicists. They call them sometimes Haram, whatever, right? So Schur multipliers are good. They're going to save the day here, plus a lot of representation theory. But, I mean, they fix at least this state. So we have one state where we have decay to equilibrium, but with a different Lindbladian. If you could implement that in Lindbladian, it might be very interesting. That gives you these kind of more stability. That is beyond. I asked Guido, who is a physics student, whether that has the physical interpretation to use this kind of Lindbladian. If there's anybody in the audience who can answer that question, see me. I would love to discuss it. I mean, I still struggle with this. I mean, but anyway, I mean, mathematically, it's not a weird object, right? Good. So here, this is one solution, and where we get something, but it's sort of unsatisfying in the sense that we are changing the object to consider, and then, what do you do? What you do is, if you cannot prove A, you prove B. So we are going to a different concept, which is weaker than CLSI, and that this is weaker than CLSI, I have to explain during the talk, and that still works. Okay. So now you take a deep breath, because we are using something else to solve to circumvent the problem, and yeah, this is something I'm working on these days. I'm not sure I should call it complexity, to tell you the truth, but it's not my fault. What happened is that I visited Jaffe a summer ago, and he was talking to me and asking me that many questions. And then a month later, he put out that paper, and now I understood why he asked that many questions. He could have told me then, but And they defined a convex complexity theory for channels. They called it complexity theory. So, calling this complexity theory for channels is not my fault, it's their fault. I'm wonderful, but it's super cool. It's just not true it's probably more closer to a logarithmic complexity than what people usually do. Here's what's happening. There are some axioms, and the axioms are super nice. If you do nothing, complexity is 0. That's the most questionable axiom at all. Does any of you have ever seen small kids? Do you know how difficult it is for them to do nothing? It's the hardest task of all. But okay, that's an axiom. We live with that. You want this additivity of complexity. So if you combine two channels, it grows, as the sum of them. You want the function to be convex. That's in the name, convex complexity, on the space of channels. And you want it to be tensor additive. And you want to grow it as most as the number of the dimension of the underlying system. So the number of qubits should be the upper bound for that complexity, and that's why I would like to call it convex complexity, because it's more the logarithm of what you usually see in other complexity theories. Okay, whether you should call this complexity or not, I don't know, but complexity just sells well, so we will keep that name, and we will go from there. Yeah. So these are very simple axioms, and they have an example which they construct using Wasserstein 1 distance, and we worked on Wasserstein. We actually have a definition of Wasserstein 1 in a 2018 paper, which nobody read anyway, and so they ignored it, but it is in there. And we have some inequalities which are useful for this project. These properties here, to tell you the truth, we can actually do pretty simple by following De Palma's ideas, right? I mean, we have, I'll see that, the first 4 properties are, if you have the right definition, they can be done we have this saying in Urbana, this can be done on a nice Saturday afternoon, right? So because, you need some space and you need some time. This one here, that's work, right? I mean, this, a priori, you don't know whether you have this logarithmic bound, but that's where this other work comes in. Okay, so here's the trick. Instead of doing Wasserstein 1 distance, we do we define a notion of complex functional channels, if you wish, if you don't want to call it complexity, a convex function of channels just given by a fixed system, a fixed set of operations. So we fix a set. We assume that the set is closed under stars. Again, that's something one shouldn't do, but that makes our life just much easier. And we take a conditional expectation of the commutator. S prime is the set of all operators which commute with all of them. And then we define a norm. A Lipschitz norm of a function is the supremum over the norms of the commutators. That's our norm, okay? So those functions which commute with all of them, they have 0 norm, right? So these are kind of either the bad guys or the good guys, depending on your choice. Then we can define actually an operator space. D by D matrices, F S tensor 1. So, I mean, it's not only a norm, it's actually an operator space. So those who actually have heard about operator spaces, if that's the part you want to forget, fine. Just, S tensor 1 you should not forget, right? I mean, that's what you do, S tensor 1. If you have a matrix, you do S tensor 1. And then we can define a dual norm. And that actually I considered even much earlier than 2018 with some other group of students. We wanted to work on a concept which is called quantum metric spaces. And then we had to work with these dual norms there as well. It goes back to non-convex geometry and whatnot. So this concept here of taking the norm as a commutator really comes from non-convex geometry, if you wish. They only take one S, though. But they take an arbitrary representation, and then if you take a direct sum, you get them all. So it's kind of a matter of choice, right? So anyway, Mr. Kohn only has one S, and that's the famous Dirac operator. If you've never heard about the Dirac operator, forget it. But I mean, it actually does occur in the literature, okay? So we have this dual norm. And here, let me tell you that I'm doing a little modification. I'm subtracting from X its fixed point, just because it's better. Yeah, that's a choice we made for our convenience. Yeah, and then so we have a norm for densities, a new norm, not the old norm. We have a norm for observables and densities, and then we can play. And in this way, if you have densities which are preserved under the dual projection, they will have dual norm 0, right? Because then identity minus E fixed is 0, so you get 0. So in some sense, every state which is fixed is free. That's the connection to Riesman theory, where you have free objects. The free objects here are the fixed point states. Yeah? So that you can view this as a resource theory without doing formal resource theory. I'm not doing this. I'm just stealing some ideas from them. Okay, good. Then I can define a complexity function or just a complex function. This is a C, right? You can see that clearly. That's a C, right? CS is phi of rho minus rho, and then we measure that in the star norm, and we take the supremum over all densities. Yeah. So since we are taking, why do I do this minus rho? I want CS to be 0. So if phi's identity, you want to be sure it's 0. Yeah. So that is kind of the standing still axiom which we impose, and that's the reason for it, right? You can then show. Oh, I have a complete version. You know me, I do everything complete. So I just tensor with identity and do it with an arbitrary system. It's kind of natural. If you want to talk to another system, you have to do that anyway. Good. Yeah, and then you check that these two things satisfy 0, 1, 3, so the first axiom. And for this complete additivity, you have to stack back for a moment. So the first system, S, was fixed for Alice's Hilbert space. The second system, SB, was fixed for Bob's Hilbert space. So if you want to talk about the complexity of the tensor product, you have to even define a set which works for both of them, right? I mean, if not, what I'm talking about is meaningless. What is the system I do? SA tensor 1 union 1 tensor SB. And I have to tell you, this union is what I overlooked in my work before. I never thought about the union. That's de Palma's idea, right? I mean, that's the right thing to do to get this complete additivity. And that's what they used in the Jaffe paper. And even though this is mathematically not hard, sometimes you have to admit, well, that's a genius idea if you want that additivity to happen. Okay? So we have all the interesting properties. What is missing is the dimension, the log dimension thingy. And that's where the hard work begins, right? So this is Todd's O log D. So here I first have to torture you with some more definition. I want to look at the worst case of F minus E fixed where the Lipschitz norm is less than 1. So some kind of operator norm between two spaces. So I call this average diameter. I also define the complete diameter by doing the complete version. And then I say that the system S satisfies Talagant's inequality. If you give me another half hour, I will explain you why I call it Talagant inequality, but that's not the talk I signed up for. So let me, I mean, I have good reasons to call this Talagant type inequality, but so that you have to believe for me for now. And then you have this beautiful estimates. Well, by definition, rho minus E fixed star of rho in this dual norm is less than the Talagant inequality of S, square root of the relative entropy. Yeah. So again, this had models before, but I believe this should be true. But it's the square root of the relative entropy which occurs. Why is this important? Well, you have some weird system. You want to measure your system with some given resources, and we will find some examples which are natural later on. And this is a universal, this is a star missing, this is a universal upper bound. Right? So the Lipschitz constant is related, the dual Lipschitz constant is related to the relative entropy. And by the way, that is equivalent to have very good concentration type inequalities. And that's the other talk I'm not giving. Yeah. Concentration type inequalities tell you can be dually formalized in this way. And if you are in dimension D, then the relative entropy is log D. So that's a reason to see the log D, right? But you see the square root of the log D, not the log D. Okay, the complete Talagant inequalities do this all with entanglement, no problem. And then we have some results for universal constant. We can always estimate the Talagant inequality by the average diameter. Yeah, that is not a trivial proof. This is in this 2018 paper with Li Gao and Nicola Corrente. Yeah. Then we can estimate the CB inequality, the CB Talagant inequality by the cardinality of S times the CLSI constant of the corresponding Lindbardian to the minus 1/2. So CLSI inequalities for a fixed set give you estimates for the Talagant inequality, and then if you have that, you get that the complexity is estimated by the Talagant inequality square root log dimension. So we are going into the O log D direction, but there's a square root and there's a Talagant inequality here, which somehow seem to not match exactly. Okay, it's time to match it. Here's the example which everybody has in mind. What is my set S? Well, I start with X and Y. These are the standard Pauli matrices, right? 0, 0, 0, 0, 1, 1, and I. X is the Pauli matrix, and Y is the corresponding other Pauli matrix with i's, right? We take all, we are taking all their positioned in different registers, right? So they're a representation. So we have 2n of those guys. And then we have a corresponding Lindbladian, which if you do the calculation happens to be this guy. Oh, I did the sign convention differently. I followed the physics here, but anyway. No, it's fine. No, it's right. It's fine. It's fine. This is the Lindbladian. Now, if you take only one pair of xy, they satisfy CLSI by tensor stability. You have CLSI for all n. So the CLSI constant is bounded below by a universal constant. That's actually pretty simple to prove. So what do I get? The complexity on an n-dimensional system is less than the cardinality of that. This comes from the relative entropy, square root of the right? That is the relative entropy. So this is square root of n. This is square root of n. It's n. So the O log D, in this case n equals D estimate, is actually the product of two things. The boundedness of the CLSI constant and the fact that I have two n many generators. Yeah? So that gives a reproof for the O log n estimate for in this particular system, and it's a model for getting all of these estimates in the future, right? So I can get abstract tools which guarantee axiom number 5, the dimension count. Good. How am I doing on time? I have 10 more minutes.
Until 26. So
26. Perfect. So before I go on to n equals to infinity again, right? I mean, I have a little aside for you. So I start with the Hamiltonian summation pj hj, and I assume that the infinity norm is less than 1. And then we found this paper by Mr. Campbell, Q drift. He calls it Q drift. I think I found a more recent Nature paper, again on Q drift. So they're doing an alternative to trotter simulation like this. So we are given our H as a linear combination of some building blocks, Hj. That's natural. I mean, many Hamiltonians are given by linear combinations. And we have some weights. We are assuming the weights are positive and lambda is their sum. We choose a very clever parameter, t times lambda over n. N is the number of iterations we want to apply. And then we define a channel, a random unitary, pj over lambda, and we conjugate with the building blocks. Yeah? Well, with the unitaries coming from the building blocks at time tau. That's a very natural operation, in fact, right? I mean, you know, if you can implement the building blocks, you can also imagine small unitaries with them. Often. Whether that's always the case, well, okay. But, you know, this is a fairly nice channel. By the way, this is a random unitary, but not a unitary, right? I mean, it's not a unitary channel. And then you prove that these two in the CB norm, or if you like the diamond norm, they differ by 2 times tau squared. Taylor series. Everybody can do that. You just have to choose these parameters right, okay? But that this is useful and actually competing with Taylor, some of the trotter formulas is a good observation, right? I mean, you know, trotter is good, but if there are other things, and they have nice properties. And then, you know, if you now, this is ETH, you have to T over N. If you do N times, you get N times that constant, and that here is lambda squared T squared over N. So if N goes to infinity, that still goes to 0. So that's why I called it epsilon N. That error goes to 0. Fine, no? So we can do an approximation of unitary conjugation, or, you know, the unitary given by a Hamiltonian, something people care about, by a channel. An n-fold product of certain random unitaries. Yeah? So that's the approximation procedure. It's a good approximation. There are some nice observations. If you fix this tau and you look at a certain state, then what you do is this channel, phi tau, if you iterate it n times, it essentially just moves your state with random unitaries and then does a classical average. So if you have classical resources, you can really think of them as random unitaries, and then you choose your classical noise correspondingly and average at the end, and you're happy. You know, so it's kind of natural. I mean, I think this is implementable to what I understand. And then my idea is, well, take these building blocks as your resource set, right? If you have a Hamiltonian, you should define your resources according to the data and not just blindly in the world. So if I choose that one, well, then I can estimate that the complexity just grows linearly. That's what you expect, right? If you choose the right resource at t equals 0, you do nothing, and then it should grow linearly. That's what you should expect. And then we ask ourselves, do we have a lower estimate? Well, no, not always, because you could be super stupid. H1 minus H1, H2 minus H2. Imagine, I mean, this is actually, I like this Gedanken experiment, right? Imagine that somebody gives you some HJs and you don't know what they are, and they trick you and give you a trivial channel to approximate, right? The unitary evolution could be trivial, but you only have the PJs and the taus, right? And you don't know. So you could try to do something trivial, but you don't know it's trivial. I like these kind of paradoxes, right? And then what happens to your simulation? Will you discover it's trivial? No. So if you have actually an H which is non-trivial, you can still find complexity arbitrarily large. And we have another result that even if the Hamiltonian is trivial, you can still have large complexities happening. Like with another constant, but kind of the constants are much worse, right? So I don't know what there's a constant. No, L, right? So what I'm saying here is that if your Hamiltonian is not trivial, that's the nicer situation, what you will observe is over time, you find this linear picture, this linear growth. We can prove that you find linear growth of the complexity with the given resources. Okay, we can only prove it with low probabilities, and if these L's are duadic numbers. We are not able to prove it, linear growth for all L. And it happens with low probability, and you can find easy examples where the probability could never be bigger than a half by doing some kind of trivial cancellation. So we are ignoring trivial cancellations, which of course an experiment wouldn't, but if you prove a theorem, you don't know what the HAs are, so you cannot decide a priori that they don't cancel. What does it mean not to cancel? Right? Anyway, so if you have a non-trivial Hamiltonian, you find linear growth. And if you don't have one, you find a worse lower estimate. Might not be linear growth. But of course, at some point, this saturates. Of course, well, that's also what we have to prove. But we can prove that. So at some point, that saturates. And that is the picture we have seen from these Brown-Susskind type conjectures, right? They have a complexity theory, and that is supposed to grow linear and then go to a saturation point. And that is the similarity we have. It's just that our saturation point is logarithmic and not exponential. Right, so but take the exponential and use anyway. But it is the same phenomena that you have a maximum complexity you can reach, and you can show on these statistics you would see if you find unitaries which witness this kind of large complexity, and we even know in some sense what is the x which does it, right? So we have we know how to measure it. In principle, you could actually lay down a scheme, and if you show me this linear growth of the growth of the length, then you have proof that you have found unitaries which are hard to implement. Yeah, it's really a certificate. You can create a certificate out of that which tells you, I did something hard. Now, whether you solved a big problem, I'm not saying that, but you can at least certify that you didn't produce trivial gates, right? And as trivial as that sounds, it's not trivial at all, right? I mean, how do you certify that you didn't do something stupid? Well, we do this all the time, don't we? Try to do this all the time. Certify that we didn't do something stupid. Anyway, here's a practical way to do that, and you just would have to look at the statistics. We have not done simulation. We should probably do that. Okay, good. So we have some results from finite groups. I will make that very short. We call it average diameter because if you take a group and a generating set, the thing you calculate is the average diameter. That gives the name. We have results from compact Lie groups. I want to be very, very short about this. So if we start with a compact group and a system which generates brackets, right? Then we can prove these CLSI bounds for all representations. So what we find is a uniform bound on CLSI constants for all representations. So that's what I want to take away. So this gives you many, many systems where my machinery with the Talagon inequality works, right? Because we have Talagon inequality, we have a fixed number of generators, we win. Yeah? They're even a little bit better than we expected. And so, yeah. So even we can control some average diameters. So representation theory of compact groups gives you examples for good resources. That's what I want to take away. Maybe I should have written just that slide. Representation theory of compact Lie groups and Hermander system gives you good resources. That's what this slide is about. And then of course, you go back to these collective noise, because that's collective noise, by taking tensor product representations. Good. Let me spend the last 5 minutes, so this is just kind of, commercial. We have some tools to get these estimates, which usually are hard. But we also know that by result of Gao and Uzi, every self-adjoint generator, even symmetric generator, has CLSI. So we have many resources where that works. Good, but now we want to go back to this noise model and send n to infinity. Yeah, we take the row-Lambda state. That was the infinite tensor product of these lambda, no? Good state. We take a resource set, which is given by summation ajj, summation aj star, aj star. Well, these are highly unbounded operators, but a commutator with that being finite happens very often. No? So it's okay to have an unbounded operator that actually all the unbounded operators in Mr. Kahn's theory are all unbounded, right? So that's not unusual. Whenever you have a channel, which somehow, if you reproject onto the fixed point state is a 6-point set, then the complexity of that channel is bounded by a universal constant. Why? The diameter is bounded. you can prove that the diameter is bounded. That is a part of the beta to 0 equals 0 to beta positive, which works, right? Spectral gap goes down. CLSI goes down. Diameter, that remains. So we have finite diameter, and then we can send n to infinity. We have finite complexity. So what do we get here? Well, if you now look at tensor products of n lambda factors, right? You take the reference state, it's the conditional expectation on these reference states is always the same. If you take this trick with the union, right? Our resource theory is the union of these two sets, right? So for every n lambda, we have two, and then we take the union of those. We find a complexity theory which can only grow c times n, right? For n copies. Now, this here I wrote s, but I should have written Sn, right? This is incorrect. Sn, because I'm taking the two here, the two there, the two there, the two, and then take the union. I told you the union trick was the right? So with this Sn, it grows by c times n for every channel. Or in other words, we are counting n lambda bits, right? If you find a channel which achieves c times n, you have verified that there are n bits of infinite dimension, right? I mean, type 3 dits. Well, I know it's hard to imagine, but what is infinite dimensional complexity? I mean, they do try to do this, and where some of the motivations to do complexity theory is the relation to ADS-C CFT, right? Which are type 3 wonder factors, which are generally, infinite dimensional. Boundaries of algebraic quantum field theory, which occur if you do this properly, they're infinite dimensional. So finite dimensional matrix algebras are good, but not really always sufficient to understand something like the boundary of a black hole and the complexity there, whatever it is. Which, of course, I don't know whatever it is, but nobody does, I think. Maybe there are some exceptions. But anyway, right? I mean, if you want to go there, you have to deal with infinite dimension eventually, and here's at least a manageable example where the complexity counts the number of infinite dits you have. And an infinite dits is this kind of, state on a type 3 lambda factor, right? And then you want to count some channels or some state there. Thank you.